Greetings, everybody at nodes everywhere in the world.
Howdy.
I'm Mike Morley,
I'm Pete
and
Tunkus.
that's Pete Tungus. And we're wearing toques because we're in Canada.
Indeed, as one
Indeed,
does.
as one does when you're in Canada. Um, so today we're going to talk to you about a subject that we are really excited about. And it's something that we, in the context of the work that we do, we have a roundtable that exists inside of Arcurve. And so what we do is the roundtable is a forum and where we share ideas with the data scientists and kind of do interesting things. So some of the things that we've been doing through the course of all of this crazy last year have been doing some experiments with Neo4j in the context of modeling physical systems. So I have a background in mining engineering, so this is an area that I'm quite interested in and have spent a lot of time working in the domain of mining, geotechnical work, environmental work, um, numerical modeling for groundwater systems, and all these sorts of things. And one of the fascinating things for me is when I saw Neo4j a number of years ago, it was just this amazing revelation in terms of capabilities that we can bring to the geosciences domain. It's actually interesting. So if you go back in time a bit, I don't want to date myself too much here other than with the old machine that I got behind me there. But when I started out doing some of this machine learning modeling in the domain of mining in particular, there was a time when relational databases were considered to be a disruptive technology, believe it or not. And this is actually a shot of, it's before even PowerPoint was a thing, slides from a session that I was at that was actually talking about, wow, this relational database thing, is this going to be a thing? Should we keep using our file-based databases? What are the limitations of relational databases? And there was a huge debate about this at the time. So it's been rather fascinating to see the same sorts of things kind of going on as graph has become more and more pervasive, but we still see these types of debates happening. Now, the fascinating things about this is we went ahead and adopted relational technology and unified it basically with the work that we were doing in the mining sector at the time. And what that enabled us to do was transcend the limits of the actual the types of modeling patterns and paradigms that were in place at the time. And you can see these were some of the machines that we actually worked on. And this is actually a model of a mine in the US that was rendered in 1989, actually. And what this enabled us by saying, yeah, relational is going to be a thing. We're going to use this stuff. It brought all these new capabilities to the forefront, where we were then able to take these complex ore bodies, and these renderings are obviously relatively low resolution to what you're capable of doing now. But at the time, they were pretty revolutionary. By combining this relational stuff with this 3D stuff, you could suddenly get an amazing visual representation and also a physical representation of the complex underground objects and other sorts of paradigms like that. In this particular example, what had happened here is you're seeing the red areas are drifts, the red and green areas. The red area would be an upper drift, the green area would be a lower drift. These are the areas where you actually would walk around in the mine underground. That cyan area was actually a collapse. So an ore pass that actually started collapsing, and it was jeopardizing the workings around the mine. These are, safety is a huge thing with this. Hundreds of millions of dollars in potential impacts to the mining operation. But by having the tools that we did, blending the database technology with the 3D technology and the geospatial technology, we were able to construct a model of this using an early version of LiDAR to scan the point clouds. And I wrote an algorithm that took the point clouds and turned them into this mesh that you see. We were then able to do numerical analyses on these to figure out exactly where the stress was being projected, how to mitigate those stresses, and then how to reroute the ore pass so that it wouldn't cause and jeopardize the operations. So this was the kind of innovation that was possible then. Now, you look at what's happened with graph, and I look at this and I'm just like, whoa, there's so much potential here. Not only like in the world of relational, as everybody out there in nodes land would obviously knows, data doesn't come in squares. No matter how much they teach us engineers that data is a box, it is not. And when you're modeling physical systems, data is very complicated, it's highly interconnected, and there's a lot of relationships in it. As Emil was saying this morning, it's the values in the relationships. And in the world of graphs, the beautiful thing about it is when you look at an ore body model or a geological model or any of these sorts of other things, the way they're actually done is you're connecting up nodes and relationships into physical structures to represent the things that you're actually modeling in the real world. So what this means is we can create with graph, because you can assign Cartesian and spatial coordinates to the nodes, you can do things like I can create a model of the surface. I can create a graph model of the road networks. I can create graph models of building structures. But I can also create graph models of boreholes, so subsurface structures. I can create graph models of mine meshes that represent the ore. I can create models of the geochemistry that exists. I can create models of plumes that exist for contaminant flows. Then I can also bring in all the rich machine learning and algorithms that are associated with the analytics piece. I can bring in all my knowledge and metadata associated with the decisions that were made to construct these models. It's a very disruptive paradigm. So over the past year, we've been basically conducting experiments to kind of pull different aspects of the world of geosciences into the graph and try them out to sort of see if we can validate this hypothesis about graph being disruptive to this world. There's some very powerful tools in this domain, such as this Meyer Geosciences Geoscience Analyst, which does a lot of the numerical modeling that's associated with mining. So what we did is we took that mine model and projected that into Neo4j, and you're seeing this rendering down here is actually directly projected off of the graph database, that exact same model. So this led to this hypothesis, can we model physical systems in the graph? And more importantly, this is coming at it, and we're trying to conduct experiments in each one of these aspects of a physical model. Subsurface borehole modeling, geology, wells. Can we unify the surface and subsurface data into a single unified model that represents everything that's on the surface and everything that's below the surface? Then can we get in sort of the field logging, characteristics of observations, samples? Can we do surface analytics? We haven't done any experiments or investigations yet in numerical modeling. Some of the work that Will Reynolds has been doing, we've tried some experiments with this as well in terms of bringing in buildings and infrastructure. In the case of the particular experiment we're going to show you today, what we wanted to do was take some of the stuff that we had, the data that we've got from the Alberta Energy Regulator, particularly with respect to characterizing, using some of the surface and subsurface models to characterize abandoned wells. So this is a big problem here in Alberta in terms of the wells that have been abandoned, trying to figure out which ones of these are causing risks, which we should look at first to try and remediate and fix. It's also a growing problem globally, particularly in the United States, with all the fracking activity that's gone on through the last 10 years with the acceleration of oil and gas production there. There's a massive and growing issue with this sort of a challenge with respect to wells that are just being abandoned and trying to fix the problems that exist with those things. So the way this process of remediation typically works is you'll have a bunch of information that's collected about the sites themselves that's stored in these sorts of field data collection applications. And we have a partner called Pura that we work with who've helped us out with this whole model in terms of being able to understand the nature of the wells that are out there and then characterize them in such a way we can make decisions about which ones we should try and address first in terms of fixing them. So the data that's collected from this type of thing goes into a model, so a site characterization model, that a knowledge graph, so we would call this an environmental knowledge graph. And basically this represents the surface location where these things exist, the metadata that surrounds them in terms of the types of production that was happening at that site, any of the historical activities that we can get our hands on, financial data if there's any, and then incidents, so things that may have happened, if there was a spill, if there was some contaminants that landed on the ground. Then there's a subsurface characterization. What sorts of constituents exist there? What do we have? Sand, which is highly transmissible in terms of if something gets spilled, or do we have a clay bed, which would be a barrier to the transmission of contaminants? Then what we do with these things is we thought, okay, well, we're going to try and experiment with this. Can we use graph data science methods and the richness, the power of the relationships in the graph to conduct a site characterization model, basically taking the data that exists from historical activities on these oil and gas sites and then running this in such a way that we construct a model out of that would allow us to make predictions and prioritize things from a risk standpoint in terms of which well sites should be the ones that we should look at first. In terms of constructing the model itself, what we did is we took in, there's a bunch of public data that's available on the Alberta Energy Regulator site in this case. The data is in a whole bunch of different forms and formats, mostly various text files, CSVs and ASCII text files. So we used a combination of some of the technology that we had developed in the prior company that I had known before it was acquired by Arcurve back in November. So we used some of that, which is basically decomposing these data sources down into atomized messages that represent the key nodes and relationships that exist. Those were projected into a graph database knowledge graph. Some of the data in this world tends to be unstructured. So this is another really interesting challenge that you run into when you're working with environmental data in particular. Is that a lot of times it gets trapped in things like reports and documents. So in a lot of cases, you have to go through and actually extract those data manually. Now, the good news is we do have processes now that allow us to take sort of environmental reports and go through them using a series of knowledge agents that basically have smart OCR processes that look for well logs, data tables, and other sorts of artifacts. And we can actually extract those things out using a mostly automated process and then incorporate the outputs from those into this knowledge graph. So our core hypothesis was, can we classify abandoned well sites using historical data to help assess their state based on comparisons to sites that had remediation challenges? We took the data from the AER and we unified that into a site knowledge graph. The other thing that we did is we did actually get access to, there's a paid data set that actually gives all the well production information. So we were able to incorporate that into this graph as well, which provides key insights and signals around the nature of the product, the stuff that was being produced. So whether it was, oil versus gas versus other kinds of side products like salt contaminated water, brines and things, which can cause a lot of issues. Projected that all into the graph, and then we started setting up a model for this. And this is where Pete's going to take over and tell you about what he came up with in terms of the first cut at constructing a site characterization model using Graph Data Science Library.
Indeed, yes. And so I'm sure that for everyone who, especially here in North America, who was up early enough to catch the keynote, right, there have been a good number of updates since the last time the Neo4j community came together in such fashion. And so we use some of that, and our plans include using more of it later. But just to kind of reiterate, some of the major challenges with abandoned well remediation in particular is that this process requires quite a bit of planning, and really it's pretty expensive, and it can be time consuming depending on the nature of the job, what's been going on at the site and so on. So it's often not really feasible to remediate wells in short order, especially when they start to build up over time, given accelerated production and that kind of thing. And so this means that we have to figure out how wells can be prioritized for remediation in some fashion. And so we propose that one way to do that is by assessing each of the wells, or in particular the abandoned wells, relative environmental risk. While there's no crystal ball out there with a countdown for a given site, if something's going to happen or not, we can at least compare abandoned sites, particularly those that haven't had any past incidents of any kind, to both active and abandoned sites presently and historically that have had such issues. And so this, I think, makes for a pretty perfect graph-related problem that can be tied into physical and spatial modeling directly. And I think that's one of the real interesting things about, the jobs that we have as data scientists, engineers, software engineers, and that sort of thing, kind of broaching in this new space because of how translatable a lot of these problems can be across different technologies. And in this particular case, right, we're finding that, applying these kinds of, or testing these kinds of hypotheses in a graph space, are oftentimes more effective and compute-wise a lot faster than if we were using a sort of traditional tabular approach. And so I'd like to start off by painting the picture at a high level first, right? So kind of following along the slide here, because initially between our two different types of wells that we're interested in, right? So again, it's looking at that green square. We're particularly interested in abandoned wells that have not had incidents. So they're clean, right? We don't know anything about them as far as any incidences are concerned. And we want to relate those and see how well they match up or how similar they are to wells that are abandoned or active, right? But that have had incidents attached to them, and that's those yellow squares there, right? But indeed, right before anything, we're not making any a priori assumptions about relationships between those two. We're just going to see what's similar, just what's out there, just pure discovery. And so after creating, engineering our feature nodes, we ran k-nearest neighbors to generate similarity scores, estimated weighted degree centrality across our abandoned well nodes, and then enhance our reporting and graph exploration capabilities thanks to weighted Louvain modularity. And so you can kind of see the evolution from our little 2x2 square. We know what we're looking at, and we have this sort of idea that there are these nodes that have absolutely no relationships a priori. And ultimately, we want to reach a state where we have these relationships between, let's say, the red ones are abandoned nodes of interest, and the beige ones are our wells with incidents, right? And so we want to be able to relate those explicitly one to the other, but we don't want to relate between clean abandoned wells or wells with incidents, right? We want inter relationships, not intra relationships. Okay, so we can go ahead and dive in then. And so Mike's going to control the screen still, and he's going to walk through some of our code and whatnot while I describe the how and why in a little bit more detail. So I don't know if this, not to bring up, there it goes. Okay, yeah, perfect. Excellent, thanks. Yeah, so again, starting with our step 0, right? The name of the game was discovery, right? So without making any explicit a priori assumptions, we must compare and discover the similarity between those abandoned wells or sites without prior incidents vis-a-vis any wells or sites that have had them, right? And so again, the emphasis is we should not assume any prima facie or a priori relationships between those two groups of wells. Rather, we want to discover those relationships, and we can base that on how similar they are using the production data, production history, geography, geology, and so on. And so step 1, right, or rather step 0 plus, right, is that we have to do what every data scientist and engineer loves doing, right? And that's munging, transformation, preparation, right? It's 80% of the work that we do, maybe more, requires 10% skill, 90% anger management. You guys know the drill. But that's pretty much the first, but that's, if nothing else, perhaps the most important step, right? And so we've already assumed no relationships, and that we'll be comparing wells, that is the nodes, in both groups based on their characteristics, that is the properties. And to help with keeping our data organized, especially given the volume of data contained in the graph, we endeavor to create feature node labels with their associated properties. This involved maintaining consistent data types, one-hot encoding of categorical and string properties, and then for the next step, combining this information into a single list type super property that ostensibly defines each node. And in fairness, this is a lot like embedding. And yes, embedding has been introduced into the GDS library, but for the first cut, we opted to try defining these super properties manually, right? So experimenting with embeddings is where we'll be going next, but it kind of gives us the option to know explicitly what's going on under the hood before, and a benchmark to test against before we move on to machine readable only type encodings. And so step 1 then, right, is that fortunately Neo4j's GDS library has the perfect unsupervised algorithm now for us to help discover these similarities, and that is k-nearest neighbors, right? And the nice thing about k-nearest neighbors is that it's agnostic to relationships and directly compares property similarity. K-NN also provides the benefit of being able to handle numerical list properties given multidimensional nodes and that sort of thing. So what we did here is we projected the feature nodes into memory, wrote similarity scores as properties of new relationships based on our 2 classes only. Again, we want intergroup similarity, not intra-group. And so the next step, right, is perhaps the most meaningful or valuable one. And so based on similarity scores, we can rank abandoned wells for risk using degree centrality. Now, the higher the centrality score, the more connected a given abandoned well is to wells with incidents. And because centrality is weighted by similarity, the score downplays vaguely similar node pairs and emphasizes highly similar node pairs. And so on its own, this already allows us to start ranking abandoned wells. But we can go one step further, right? And so step 3 is right? Because of how K&N works, as well as how we specified or conditioned our written relationships, right? Again, intergroup, not intra, right? Any output would be universal across the entire graph. And this is really okay for a first glance at the rankings to pick out, the really egregious risky wells that should be prioritized for remediation. But if we want to do anything relating back to the site characterization model or find curated and filtered groups of wells to prioritize explicitly, we can use those similarity scores again to discover clusters or communities of abandoned wells and incidences that are highly connected using Louvain modularity, weighted by, again, the similarity score. And so this helps with, like I said, narrowing the set of wells. It can streamline prioritization process if we're interested in remediating specific types of abandoned wells that are highly connected to one another. And this also translates easily into, let's say, if we need to push something to a dashboard or a spreadsheet or a tabular report, right? Both traditional graph visualizations and spatial and physical model visualizations, right? All that stuff can be integrated with the results that our system and our process produces. So with that said, I'm going to hand the mic back over to Mike, and he's going to walk through some of those neat results. And I would argue like some of these visuals are pretty freaking cool. So in any case, yeah. So
we're having fun, man. We're having fun.
Indeed. That's the beauty of these experiments, right? Because like it's low pressure in the sense that, we don't have deadlines or so, but at the same time, we're exploring and we're discovering a lot of neat stuff.
Yeah. So as Pete had indicated, so the basically the output of the combined assessment with respect to the K&N process, the degree centrality, and then the Louvain bits essentially gives you this type of an output where we have a series of communities that are generated. We have wells that are basically clustered into those communities. Those communities have various characteristics. And then, of course, there's the ranks that operate from the degree centrality element inside of the context of those communities. So this is, kind of an okay output, but, we can have some more fun with it than that. So first thing we'll shine up here is our friends at GraphXR have made this really nice gizmo that allows us to just basically see the results of the actual K&N process, similarity process. And then we can kind of demarc the abandoned well nodes inside of that. And these have been scaled by the size is the size of the rank. And then the similarity, of course, are the relationships that are hooking these things together. So I often will throw things into GraphXR just to kind of have a look when I'm doing these sort of similarity clustery things to just get a sense of, are the clusters nicely distributed? Do we have, we don't have big blobs of things, that kind of idea to get a sense of the characterization. Another really fun thing that we found is this Kepler. So we wrote one of our summer students last summer wrote a really nice little gizmo that lets us hook Neo4j directly up to Kepler. And this thing's great for visualizing temporal spatial data sets, particularly, Neo4j and this thing work really well together. So I'd encourage you to check that out. We published the source code for that up on a Git repo. So in terms of interpreting the results from this whole thing, basically what we've got is this is a heat map. Right now we are filtered down to only looking at abandoned wells. So these are wells that have actually been abandoned. These are all well types currently for the entire province. So areas where the ranks are high are demarked by red. So these would be areas where you're likely going to want to pay more attention to. And this is also for all time. So one of the nice things you can do with Kepler is there's all sorts of filters and interesting things that you can actually use in real time here. So what I'm going to do is we're just going to walk through a basic. Now, normally with something like this, we would also factor in things like companies and other dimensions. So if you're an organization who is looking to help divest the liability associated with the abandoned wells, you would basically say, okay, show me the wells that I'm responsible for, and then I can look at these various characteristics to decide which ones I want to try and address first. So let's start by doing this. Let's fire up another visualization aspect in here. So this is going to show just a little bit of a different perspective on this. So this is, again, all of the wells right now in the province, and then the heights and the colors. So the colors and the height are the same thing. So it's basically the ranking index, where red, like orange and red, are the ones that are more problematic with respect to risk, and the height is correlated to that as well. So now what we'll do is let's just look at a specific constituent. So let's say we want to look at just oil and gas, or oil wells in particular. So that reduces the data set down again, so that we can see here we've got, same sorts of things. The little guys there are ones you probably don't have to worry about as much. The big guys that are red are ones you probably want to worry about more. So then what we can do is we can kind of pull our filter back to just look at the really nasty ones. So across the province, these guys are the ones that you would likely want to try and address first according to the way this model is structured. And then because we have the richness of the graph, and we're not showing everything that's in this graph because some of the data we can't show some of the actual core production data or some of the other things because they're confidential. But the entire knowledge graph that sits in behind this would allow you to do a very detailed investigation into the characteristics of these actual sites. The other thing that we're doing here is, I think somebody else this morning mentioned using Uber clusters, BH3. This is a really useful thing in the context of these sorts of analyses, because we can aggregate data up, so fuzz it a bit if we don't want to, specifically if we're dealing with more confidential data and whatnot. So we can still do these assessments and kind of have this information rendered and not have, exposed that sort of PI. The other really useful thing with this is these H3 clusters can be used to visualize things spatially and temporally like this. But you can also pull, because they're names, you can actually pull them back into the graph and use them as a dimension inside of the graph itself. And finally, kind of tying in the last bit here, if we go in and have a look at a specific community. So let's say we wanted to look at this one here, which has got some crude oil, bitumen, water, and condensate. So we'll just take that little guy there, that Louvain community, go back to our map. Let's just go back to our filters. We'll go open this up again. We'll put our community in here. There we go. So that then is the net resulting community that we're looking at. We can bring up our date window here to kind of see when these wells were set up. And there's other dates that we can kind of do. So you can use this kind of as a nice little filter. This thing's also kind of got a cool thing where you can animate it, which is kind of nice if you're trying to show sort of incidents over time that impact, the characteristics of the way the sites have been shown and stuff. And then we can run this down again to just show our highly ranked items in terms of, okay, now these are my targets for this year's remediation program. Beauty. Back to you, Pete.
Right on. And so effectively what we've been able to do, thanks to some of these tools in Neo4j, is that we can take that list of 100,000 abandoned well nodes, or however many there would be in a given data set, right, or a database rather, and effectively, as planned, right, figure out some way to prioritize now. So, in terms of whether or not we're able to achieve our goals, I mean, honestly, so far so good. So we're still plotting ahead accordingly. And so our next steps are built around the sort of lessons we've learned thus far, along with the kinds of things that we've thought about that we want to implement in the future. And so, one of the key things, and I think this is universal to all of these kinds of projects, experimental or otherwise, really, is that it always helps to have more data, right? So more data sets to create a more comprehensive site model. And so that could mean, additional wells and more historical data, more regional geographic data, as well as, importantly, right, temporal data as well, right? Because if you're comparing present day abandoned wells to wells that had an incident, 60 years ago or something like that, or 50 years ago, or however long ago it was, the conditions under which those incidences occurred, along with the technology surrounding them, changes, right? But as you can see on the slide, we have a bit of a laundry list of that as well. But again, same with the 3D mesh model, right? We want to be able to do a better job and put in a little bit more work in terms of linking a lot of the data that we have into those mesh structures, again, so that we can work on, again, not just combining these sort of analytic these analytic capabilities in a general sense to produce reports, let's say, or prioritization lists. But again, link that back to the graph so that the graph itself is a universal platform that contains everything from those surface, subsurface knowledge elements and all the rest of it, right? And so indeed, for the site characterization and remediation prioritization experiment or sub-experiment, I would say in particular, right? We do want to tweak and enhance the feature node engineering as well as our pipeline. So that'll include things like implementing node embeddings and that kind of thing to kind of help speed the machine's ability to make those similarity comparisons and develop those degree centrality and subsequent community clusterings. There's always work to be done and things to think about as far as additional visualizations and reporting capabilities. And as we've highlighted, right, incorporating more dynamic features, right? So temporality, nature and magnitude of those incidences, any additional risk criteria that's appropriate in the context, any feedback that we get from subject matter experts and that sort of thing, right? Whether that's receptors, human proximity, land use, and so on. And indeed, historical impacts. One of the top things that has come up time and again from our partners at PIRA is that, at the end of the day, it's the bleeping liability that really counts here, right? Because again, it's a very expensive process. We have to do it and it must be done. But if there's some way that we can kind of nip it in the bud or head it off at the pass, so to say, right, and remediate the well before it becomes a real risk, right, then that's the goal. So the big takeaways are that, we would argue, as I think many of you here would, is that a graph solution to data modeling really allows integration of truly disparate data into a universal space, whether again, it's things like, knowledge graphs, spatial models, spatial databases, and information that's coming from both structured and structured databases, whether it's an RDBMS or a data lake or what have you. And again, data, what a surprise. It's a recurring theme, and we're always interested in quantity, quality, availability, and consistency. But again, these are things that you just have to work through, and it's going to happen. So one step at a time.